The sandwich theorem or the squeeze theorem also holds for limits as x approaches to plus or minus infinity as well. For example, if we have such, then sine x, again it is between 1 and 0, right? Again, the graph of sine is this minus 1 plus 1, so its absolute value is between 0 and 1. So if we do sine x over x, it is less than or equal to 1 over absolute value x, 0 over absolute value x. Since x is approaching plus or minus infinity, we know that x is not 0, so this inequality is true. So limit as x approaches to plus infinity or minus infinity, 0 over absolute value x is 0, and limit x approaches to plus or minus infinity of 1 over absolute value of x is 0. This gets close to 0, but this is always 0. It doesn't get close to 0, but it is always 0 because the numerator is always 0. Right? So anyway, their limits are 0. So this have finite limit, that is 0. So by squeeze theorem or sandwich theorem, limit of the middle one, sine x over x is 0 also. And if the absolute value of something approaches to 0, then without absolute value it must go to 0 as well. So it is limit x approaches to 0 plus or minus sine x over x is also 0. Okay, so since this has finite limit, we can apply limit law. Limit of the sum is sum of the limits. So this becomes by limit law, limit x approaches to plus or minus infinity, 2 plus limit x approaches to plus or minus infinity of sine x over x. So limit of the constant function is that constant, and this is 0 as we have showed by squeeze theorem. So that's sandwich theorem there, and we get 2 as its answer. Class number 5, continuity. Continuity at a point. Continuity at a point. So we say a function f is continuous at a point, so at C. If we have a graph of a function, let's say this is the graph at C. Is it continuous? No, it is not. We are going there, and then we have to lift our pencil to hit this point and then go again to the curve, so it is not continuous, right? So why this is not continuous? Well, as x approaches to C, the graph approaches this number right there, but my function value is different. That's why it is not continuous. So when do we say it is continuous at C? If the condition is very important. When we take the limit of the function, it must be equals to the function value at C. That's the definition of continuity at a point. So this definition requires how many things? Look at this definition, right? It requires how many things? Well, something has to be equal. So to be equal, that should exist, and that should exist, and they should be comparable, meaning that's definite number and that's a definite number, right? So this definition requires three things. Number one, f must have a limit as c, right, from both sides. And f must be defined as c. So must have a limit meaning it is a definite number. Defined as c meaning it is a definite number. So we can compare the 2 and 3, the limit. So 1, the limit should be equal to its function value 2. These three things should be satisfied. If f fails any one of the three conditions above, we say f is discontinuous as c. Discontinuous as c. Okay, so there are some various kinds of discontinuity. So if 1 is okay and if 2 fails, so 1 was limit, so limit exists, but 2 failed. 2 was f is not defined as c, then we say it is removable discontinuity. So the limit exists, but the function value does not exist. It is like this, x squared minus 9 over x minus 3, for example. Then this function is not defined at 3, but it is this, right? So the limit exists. Limit x approaches to 3, f of x is, so we can cancel this and it becomes 6. So 1 is okay. 1 limit exists, but f of 3 does not exist. So 2 fails. In such case, we say this removable discontinuity. That is because if I draw the graph at 3, 6, and it is x plus 3 other than 3, f of x is essentially x plus 3. So it has y-intercept 3, slope 1. So the graph looks like this. It is 6, yeah. So the limit exists, but the function value does not exist. It is called removable discontinuity because if I define f of x so that if x is not equal to 3, x squared minus 9 over x minus 3, and if I say at x equal to 3, I will assign f to v6. So by assigning f of 3 manually, we can make this function to be continuous. It can be made continuous as c by defining the function value to have the limit value as c. So we can make the function to be continuous by redefining the function at one single point. If that is possible, we say this removable discontinuity. Removable discontinuity also occurs if 1 is okay, 2 is okay, but 3 is not satisfied. For example, as I drew earlier in the beginning, if the graph goes like this, So let's say this is 1, and that's 3, and this is 1. So 1 is okay, limit exists. Limit is 3, that's the limit. 2 is okay, function value exists. F of 1 is 1, so 2 is okay. But 3 fails because this value doesn't equal to 3. But by redefining this function as a new value, so if I define g of x to be same as f of x, so let's say the original function was f, right? If x is not equal to 1, and at x equals to 1, we just define the function value to be 3. So by looking at this new function, we can make our example a continuous function. Therefore, since we are able to make it continuous by redefine a function at a single point, this is also removable discontinuity. So removable discontinuity basically occurs if 1 is okay. Whereas if 1 fail, then we have jump discontinuity or infinite discontinuity SC. So 1 fail meaning limit does not exist. So if we have a function like this, let's say as C, I have this branch and that branch like this. So as x approaches to C, the graph does not approach a single number, so the limit does not exist. But there is a finite gap. Then we say this is jump discontinuity. You cannot make this function continuous by redefining the graph at a single point, unlike removable discontinuity. So this is not a removable case. There is a definite jump. It is called jump discontinuity. The other case of limit does not exist is where if the limit approaches infinity or negative infinity. So as C, my graph may go to infinity or minus infinity or something like this. Then there's an infinite discontinuity SC. So if the limit does not exist, then we either have jump or infinite discontinuity. So there are 3 kinds of discontinuities. So for example, a f of x is this. If x is not 0, it is 1. x0 is 0, so that's the graph. Well, limit exists at 0, right? And if I redefine the function as single point, if I say this as 1 at x equal to 0, by redefining the function value at a single point, I can make it continuous. So limit exists. 1 is okay case, so this is removable discontinuity at 0. G, yeah. If x is less than 0, it is 1. If x is bigger than or equal to 0, it's 0, right? Well, limit does not exist at 1. It doesn't approach a single number, right? So 1 fail. So it is either jump or infinite discontinuity. Which one? Yeah, it is jump because there is a definite jump. Finite gap. Finite gap. Then it is jump. Infinite discontinuity meaning infinite gap. There should be infinite, infinite distance. But here it is finite gap, so it is jump discontinuity. So jump discontinuity at x equals to 0. C. Let X denote the amount of taxable income in dollars. The amount of tax T is computed as follows. Determine the constant C that makes this function continuous for all X. So we can draw a simple graph and examine. If X is less than or equal to 0, it is 0. Between 0 and 10,000, 10,000, yeah, 0.14x. So y-intercept is 0, slope is 0.14, so it may go something like this. And if x is bigger than or equal to, 10,000, it is c plus 0.21x. And to be continuous, they have to match here, right? So 0.21 is bigger than 0.14, so it has a bigger slope, so it is more steeper. So what is this value right there? That is c plus 0.21 times 10,000. That should be equal to the value coming from the left. So c plus 0.21 times 10,000 should be equal to, what is the value coming from the left hand side? It is 0.14 times 10,000, right? So that gives c equal to minus 700. That way, the function is continuous everywhere. Okay, so let's look at examples of famous continuous functions. So continuous at which point? We are doing continuity at a point, right? So continuity at a point was f is continuous as c if limit as c is f of c. So polynomial, what was polynomial? Polynomial was something looks like this: constant plus constant times variable x plus dot 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 up to constant x to the n, where n are natural numbers. So where is it continuous? Well, do you remember that when we talked about limit, if I want to compute the limit of a polynomial, then I can just plug in the value c to the polynomial. That's exactly this. Therefore, polynomial is continuous at each point c. At every point c, I can do direct substitution. So polynomial is continuous at everywhere, at every real number. Rational functions. What was the definition of rational functions? That was polynomial over polynomial. So again, when we did the limit laws, we said limit of rational function, limit of quotient is quotient of the limits unless the denominator is not 0, unless the denominator is 0, so the denominator limit is not 0. And since each of these is a polynomial, we can do direct substitution. Okay, so we can say this equals to that unless the denominator is 0. So because this satisfies the definition of continuity, we say a rational function is continuous where the denominator q of c is not 0. So it is continuous everywhere except where the denominator is 0. trig functions. So trigonometric functions, this is the graph of sine, right? That's the graph of sine. Well, from the graph it is evident that it is continuous everywhere. For each point, its limit and function value is the same, right? Graph of cosine. What was the graph of cosine? Cosine goes like this, yeah. So cosine x is continuous everywhere. What was the graph of tangent? Tangent was sine over cosine. So it looked like this. You have to remember all these graphs. Pi over 2, 3 pi over 2, etc. 0 pi, right? That's tangent. When is tangent continuous? Here. Not at pi over 2, not at 3 pi over 2, etc. And what was secant of x? Secant of x was 1 over sine x. So secant is not continuous if sine x is 0. Right? So you remember what's... I'm sorry. This is cosecant. Secant x is 1 over cosine x. And then what was cotangent of x? It was 1 over tangent x. Right? So we can say trig functions are continuous on their domain. Domain meaning all possible inputs. So trig functions are continuous on their domain, on its domain. If I plug in x into that trig function, then the trig function is continuous at that point x. If I plug in x as its input, then it is continuous there on its domain. Absolute value function. What's the graph of absolute value function? Yep, it looks like this, yep. So at any c, its limit is equal to its function value. So the absolute value function is continuous at all real numbers. Remember, absolute value of x can be written as square root of x squared. Yeah, and we'll use this expression later when we derive differentiation rule. Yeah, so remember this.